So in 7.6, we'll be taking a look at solving equations that involve radicals. But before we get to those problems, I want to show you the technique we'll be using and the potential issue that arises when using the technique. So I'm going to start with this statement that x is 1, right? X equals 1. Now, I'm going to square both sides, which is something we've not done in any equation up to this point. But if you think about it, it makes sense, because if two sides are equal and you square both sides, then you're multiplying both sides by the same thing. So that should be allowed algebraically. And so squaring both sides, now I've got x squared on the left, and in this case, 1 squared is still 1. Now with this, as an equation, I'll think of it like a equation that has an exponent other than a 1, so nonlinear, and so I'll factor it by moving the 1 on over, setting it equal to 0, factoring using the difference of squares, and then setting each factor equal to 0. And so notice what's happened here. Throughout this just like 4-step process, I've gone from starting with a statement that x was 1, and I've done algebraically allowable things, and I've ended up with the statements that x is 1 or negative 1. Now, that clearly, we've introduced a new solution here, right? This was not a value of x initially. So where's the problem? Well, the problem, not so much the problem, but the situation that occurs. When you square both sides, understand that when you square something, it's that thing times itself, which means you're going to lose the sign nature of that particular value, right? If you square a 1 or a negative 1, you get a positive 1. So after this step, we've lost the ability to know for certain what was here that got squared. And what that means is that can lead to things called extraneous solutions, meaning we can use this step, use this approach in an equation, and effectively generate an equation that has a solution that's not actually a solution to the original equation. So we have to watch for that. We must check any solution we ever get to any of these problems where we use this method of raising both sides to a power, specifically an even power. So other than that, keeping that in mind, the step that we will use, or steps we will use, are right here. So the isolating the radical means get the term that is involving the square root or the radical sign on one side by itself. Then raise each side of the equation to the power needed to cancel the radical. Well, let's talk about these two steps. For this first problem, isolating the radical is simple enough. I'll just add the 3 on over. So I've got the square root of x minus 9 on the left and 3 on the right. Now this raising each side to the power needed to cancel, that goes back to our understanding of if this is a square root, if you square a square root, then you get what's inside. By definition, squaring a square root will give you what was inside of that radical. So from that step, I'll take both the left side and the right side and square both sides, canceling the square root. The square root of x minus 9 squared leaves me with just x minus 9, and the right side gives me the value of 9. And then lastly, you've got now a very simple, in this case, linear equation. You can just add the 9 on over, get x equals 18, and you have the potential solution. But now you must check the solution. You have to take this value, go back to the original equation before you did anything, and check it. So that's going to be square root of 9. So that'll be 3 minus 3 equals 0. So that does check out. So 18 would be the solution. So in that case, we did not end up with any extraneous solutions. Now, when it comes to squaring both sides of an equation, we do want to recall a very, very important idea that we discussed in probably back in the chapter on polynomials, where if you have we'll call it a binomial, but any set of multiple terms, right, more than one term added or subtracted together, and you square that expression, it's not as simple as squaring each piece, right? If you square a binomial, you cannot just, you can't think of it as distributing the squaring. This has to be thought of as a plus b times a plus b, right? That's the requirement. It'll never be the case that this would give us that expression there. So with that being true, we just need to be careful in problems like this, where as we go to do step 1 and isolate the radical, we will subtract that 5 right there on over to the other side and get 2q minus 5. And so then the next step is squaring both sides. So I'll take the 4q plus 5, the square root of that, and I'll square it. And then over here, you have to make sure you write it as the whole right side squared. You cannot just say square each piece or square each term. That's not mathematically the same. We're squaring the left and squaring the right. And when I square the right, I'm going to go ahead and write it out. We have to make sure we understand that that's what's going to happen. Now on the left, squaring a square root, we have just 4q plus 5. On the right, though, we've got a 4q squared minus 10q minus another 10q and plus 25. And now, with that, we notice since we've got a q squared, this is not a linear equation, so our approach would be set equal to 0 and factor. So I'll be combining like terms along with moving this stuff over, right? Subtracting a 4q and subtracting a 5. So 0, nothing left on the left side. There's a 4q squared. I got minus 10, and that minus 4, so minus 24q and plus 20. And then for factoring purposes, the GCF will be very, very helpful here because that not only reduces the numbers, but simplifies that down to a easy case trinomial rather than a bottoms-up scenario. So numbers that multiply to a positive 5 but add to a negative 6 are negative 1 and negative 5. So I get q minus 1 equals 0, and q minus 5 equals 0. So I get q equals 1 and q equals 5. However, we have to check both of those solutions. So checking q equals 1. Again, make sure you go back to the original equation, the initial thing we started with there. So that'll be 4 plus 5, so square root of 9. And so we're looking like 3 plus 5, so we're looking at 8 equals 2. Well, that didn't work, so that's not a solution. Now, we'll check q equals 5. 4 times 5 plus 5, then the plus 5 on the outside of that radical, and then 2, my goodness, 2 times 5. So plugging 5 in for both the places q existed. So got 20 plus 5 is 25. Square root of 25 is 5. And that is looking good. So the only solution to our equation there is the value of 5. So if we run across equations with multiple radicals, there's a couple different scenarios. We're going to go with what I'll call the simpler, more straightforward ones. If you ever get an equation with multiple radicals, it will just be the case that you'll have one radical term for each side, or if they're not on the same side, or if they're on the same side, you want to separate them. We want them separated, but notice you can also in this case, and this is really the only case in this class you'll see this, you can see things other than square roots. So in this case, the fourth root. That's why the directions were written in the way they were, because we said we raised each side to the power needed to cancel the radical. Well, in this case, with a fourth root, I need to raise both sides to the fourth power. Like so. And then that immediately simplifies, and we get y plus 8 equals 3y. This is a linear equation. So subtract the y and divide by 2. And then we will check that solution. The fourth root of 4 plus 8 equals the fourth root of 3 times 4. So the fourth root of 12 equals the fourth root of 12. So that looks good. So 4 will be our solution. All right, the other one here, they're both square roots. This 2 out front, the thing about this, when we say isolate the radical term, we want to make sure and point out that this is still one term. It just has a number out front of it, and there's no way to really get rid of that 2. The only thing we could possibly do is divide by it, and that would just put it in the denominator over here, just to probably as confusing, if not more confusing. So we look at both of these and recognize they are square roots. So again, with that step of raising both sides to the power needed to cancel, we know that that power is a second power. So we would take the left and the right side and square both sides. Now, on this left side, when you square this, notice this is one term with multiple, if you could call them factors, 2 times that root x. Here, when you square this, you can think of 2 root x times 2 root x. This is the place where you are squaring each piece of the term, right? These are not separate terms. So you actually do get a 4, and then the square root of x squared is x. So that's how you would square that one term there. And on the right side, you're squaring the square root, so you just get what's inside. And then from there, we start solving for x by subtracting and then dividing, and so we get a value of 3. So we will check our value of 3 here. So 2 times square root of 3 equals the square root of 3 plus 9. So 2 root 3 equals the square root of 12. Those don't look the same, but if we recall how to simplify a radical, if I think of 12 as 4 and 3 and 4 is 2 and 2, then 12 is 2 times 3. And we know that for a square root, that pair of 2's will come outside. So the square root of 12 is 2 on the outside with a 3 on the inside. And so that did check out. So that means 3 is our solution.